speaker is Charles Dunkl.
Well, good afternoon. Thank the organizers for inviting me to. I almost feel like a bit of an outsider here, since I was never Dick's PhD student or his they invited me anyway. I went to take a look, which is sort of a broader view that I wanted to talk about how Dick created this giant group of people who learned from each other, who went to meetings together, he influenced all of us in some way. We benefited from being in this group of people influenced by him. And that's sort of what I would like to talk about. The pictures that were shown during the intermission of the various conferences, some of them could be illustrations for events that I'm going to mention. So let me start with, I will start with the beginning. How did I get to know Dick Askey? What kind of events showed up that were important? This is about the same thing as going to various meetings. What did we learn from Dick? He always looked, I think, for important properties, not trivial identities or silly generalizations of something. So by listening to him, we got ideas of what is things worth looking at. Positivity is very important. Connection coefficients. I think Dennis just mentioned that, in fact. And of course, hypergeometric series. And there's a lot of people involved in my talk. Went too fast. So this takes place over 58 years to today, because it all started in the spring of 1964. How did we get into this? So as a sideline here, why are we in special functions? So here's some tips to look at to see whether or not you're in the right place. In high school, you were really good at proving the trig identities. You love trig identities. You like the formulas in physics, but you may have been asked to stay out of the chemistry and physics labs. Chemistry, I only set fire to my hair once. In the physics lab, I blew up a thermometer which disappeared from view. I was trying to drive air out of a glass tube and it was already sealed. And you may have heard the story that when a mathematician walks into a chemistry lab, test tubes break spontaneously. So I think that's part of it. In complex analysis, we really enjoyed summing series and finding definite integrals with residue calculus. In fact, Dennis just mentioned the integral for Askey-Wilson. And I just remember seeing the pictures, go around this pole, avoid that pole, and so forth. But it's a really great technique. Like differential equations, it was preferable if they had exact solutions. Eventually, we got introduced to Fourier series, integral, convolution, summation kernels. I thought of one more thing, which is maybe going to get me on a blacklist. If you have to use the axiom of choice, it's not a proof, but let's let that go. How did I get to Madison? I was working on my master's in Toronto and got to see Rudin's book, Fourier Analysis on Groups. I really liked that. And I wrote to him, asked if I could come and work under his supervision. He said, yes, I could. And maybe to my shock and surprise, the problem he gave me had nothing to do with locally compact abelian groups, but it was about spherical functions, Gegenbauer polynomials on the sphere and their convolution structure and things of that sort. In Madison, I took just one course from Rudin. It was analytic number theory. He was someone who really liked to keep challenging himself and learning new things. I also, as I mentioned about Madison, that people told me that it was such a big department that you could find 5 people who didn't talk to each other about mathematics, that there was so many different groups. Since I needed to work with Gegenbauer polynomials, Walter told me to go take Askey's course. And that was in the spring of '64. And then ever since then, I've been interacting somehow with Dick. One of the first things he mentioned or he taught us was you need to know the literature. He was famous for that. At one seminar, Walter Rudin said to everyone, Ask Dick, he knows the literature. I showed this at the Askey 80 conference, but if you haven't seen it, this was the beginning. I also tried to find out the inflation factor. I paid 35 cents for this notebook. I think a spiral notebook right now is about 10 times, but maybe not. You notice that the first page is all about the gamma function. So I would like to suggest the gamma function is the second most important function. Walt Rudin said the exponential is the most important. So I think gamma is the second one. We had a lot of problem sets in Dick's course. I generally got all the answers except powers of -1 and 2. I still have trouble finding them. And these days I run things through in Maple to see if I got the right sign somewhere. You know that if you're doing anything with Gegenbauer polynomials and so forth, sooner or later there will be a power of -1 or a power of 2. Dick told me to look at papers by Kogbetlians and Paul Schmieder. I think these were about summation of Gegenbauer series. I got my PhD, went on to an academic career, worked sort of in abstract harmonic analysis. I had some things to work on. Eventually, it was sort of not really going very well. Found out that one needs a network. In those days, you couldn't wait for the papers to be published because it took years. So you had to have friends who would send you preprints. Got interested in looking at orthogonal polynomials in harmonic analysis context. For example, here's a trivial one. If you expand a positive definite function in spherical functions, you must have non-negative coefficients. You know, it takes no proof once you find out it's positive definite. The first important conference was the one in Blacksburg, 1974. I think there was, at least for me, an extremely important conference. Dick gave a series of 10 lectures, big things like connection coefficients, positive expansions, integral formulas. Gasper reviewed the proceedings. The author shows how useful special functions are for solving various problems, and this is the main thrust of these lectures. Dick's quote, "One studies special functions not for their own sake, but to be able to use them to solve problems." I almost disagree with this partly. Sometimes there's a lot of fun to be had by just finding something and proving it. Who were there? George Gasper, Murad, Willard Miller, and I think I may have overlooked George Andrews, who I think in his talk this morning said that he was at this conference. So I apologize. I guess I was not talking to the partition theory people because I didn't even know what that was. Because it was the summertime, it was a family event. A lot of us brought kids. They played around in the hotel pool. I also met somebody older. Izzy Hirschman was there. It was very nice to meet these people and get to know them. The next important conference was the Mrc Conference that many of us went to, I guess. Askey, of course, was the editor. And so this is where he said, "Oh no, we're still working on theoretical special functions, that the computers are not doing everything that can be done, differential equations and so forth." I don't know, nowadays with these big data things, they're back to just crunching numbers without having any analytic structure, practically, it looks like. Up the list of speakers, which I reproduce here because it's very impressive that these people who were there and the different topics, Gauci and computations, he gave algorithms for finding the three-term recurrence, knowing the measure. Frank Olver, Bruce Berndt, George Andrews, Neil Sloan, Carlin McGregor, actually 2 talks. Ken Case, Willard Miller, Loyal Durant, George Gasper, Tom Kornwinder. Especially, I know this paper, the 2 variable analogs. I think this was pretty fundamental in further work on several variables. So there are many citations came from these papers, as one can find. And of course, we had great chances for meeting people. We all remember the famous April Fool's slide by George Andrews. He puts one transparency on after another, and we were getting more and more astounded by stuff. And then finally he says, "April Fool." Well, yes, it was quite something. And then as we were trying to leave, March 31st, there was a giant snowstorm, which is typical of Madison. Whenever you want to get out of Madison, some stupid snowstorm. It's like Askey 80, another conference, I found out about Tom Kornwerner's theorems and got interested in addition theorems. What is an addition theorem? You start off with a compact matrix or finite group, a closed subgroup, which has a multiplicity-free property, so that any irreducible representation of G has at most one vector fixed under H. This SON, the symmetric, the special orthogonal group, the unitary group mod n minus 1, and this is the symmetric group on N, and this is the subgroup that fixes either the first K and the last N minus K elements. H invariant vectors normalized to be one at the identity of all the spherical functions, and GH is called a Gelfand pair. One reason we like them is there's a product formula which manifests for Gegenbauer polynomials, Jacobi polynomials. What is the addition theorem? You write down this function of H, the subgroup, for arbitrary fixed elements of group G1, G2, and express this as an H Fourier series. So the first example of the addition theorem is the well-known Gegenbauer polynomials. The second one for the unitary group, that was Kornwerner's theorem for Jacobi polynomials. The third one, I did that for Hahn polynomials. At an Evanston meeting, I think this was actually mentioned before somewhere today, George Gasper said, I should look at Croucher polynomials. Everyone had done continuous. What about discrete? The group to do is you take the wreath product of symmetric groups. So you take n tuples whose entries are 0 to k. You look at the subgroup which fixes 0, 0, 0. This is a Gelfand pair. I found the addition formula for the Croucher polynomials. These are orthogonal with the binomial distribution. I wrote the paper, published in the Indiana Journal. Dick reviewed the paper. I quote, notice I say favorable both for American spelling and English spelling, okay? Canadian spelling as well. Unfortunately, the author carefully avoids hypergeometric function notation, and as a result, his addition formula has a slightly less elegant form than necessary. Well, that was his fault. You know, he didn't teach me hypergeometric functions in his class. So when I visited Madison in 75, 76, he said, bring a yellow pad, come to my office, sit here, and gave me about a 2-hour beautiful lecture on everything I needed to know about hypergeometric functions. I got some great notes out of that. In fact, some of them wound up in the first chapter of my book with Yuan Zhu. I got recalled to the factory, I think one could say. Justify my whatever, to show I've learned something, I'm producing the addition formula with the correct notation. So here's the Croucher polynomial. It's a 2f1. Here's the addition formula. It is a double sum, like Tom Kornwerner's addition theorem was a double sum. So all these are bounds, and because the space is discrete, there's all sorts of nasty little, well, it takes the max of S, the minimum of S in minus T, and so forth and so on. But in any case, it's a double sum. Here's some bunch of Pochhammer symbols. So here's sort of the two main terms, two Croucher polynomials. And yet there's another one more, a 3f2. I didn't name the 3f2 because it's two different Hahn polynomials, depending on is S minus L bigger than N minus T or smaller. In the special case, if P is 1/2, then the group is just S2, so just 0, 1 tuples, and it's a single sum. So the second term here disappears, and also that one, this KL disappears. I have to thank Tom for the idea to use groups, and George Gasper for telling me to go look at these polynomials. Again, I like to emphasize that these are people I met because of Dick. It's part of the group. The Q disease shows up now, and George Andrews were looking at, well, we've heard about this already, Q analogs of the classical orthogonal polynomials. I didn't think this was very easy. It was already, there was a lot of parameters floating around without going to Q. There's different approaches. The historical number theory, where Q is variable, the information is all in coefficient. Then there's harmonic analysis, where Q is a prime power, and you look at matrix groups over the finite field characteristic Q. Then another manifestation is quantum groups. I'd like to say that's Greek to me, and it still is, but I had Greek in high school, but it's an analog of that. I still couldn't co-multiply if you gave me $10. I just don't know. I've seen papers where people use Q and they say, oh, this is quantum. It's not quantum theory. They're abusing the language. And I think this was another example of Dick's concept. Put in more parameters, might make it easier to solve. It becomes more interesting. Wanted to do something myself. So I looked at a Q-Han polynomial, which I got to know about because they sent me the mimeographed notes for these things. So I need a spherical function structure for this Q-Han polynomial. I take the finite general linear group with Q elements with A plus B. The H is a subgroup that fixes a subspace, so it's triangular, makes everything more complicated. So general linear down a diagonal, and this is just plain old matrix over here. The homogeneous space is a collection of eight-dimensional subspaces. We need a spherical function, so we can do an addition formula. So here is the Q-Han polynomial. I put something in front of the 3p2 and I called it E, and I fall prey to what George Andrews wrote in one of his papers. In Q, there's as many notations as the number of writers. Maybe that's cut down some, but yeah, I'm guilty. Spherical function is with two parameters equal. This comes from work of Philip Delsart. Q-Croucher polynomial, called affine Q-Croucher polynomial. It has, for people who haven't seen this before, why is there a 0 here? Why isn't it 2phi2? Because the 2phi2 has another bunch of Q's sitting in there when you write down the power series. So you have to call it 0. So this is orthogonal for something like the binomial distribution. This is what my addition theorem looks like. It doesn't come up right away. We need endless bounds for the triple sum. Don't try to memorize them. And this is the addition theorem. It is a triple sum, Q-Hans. These are Q-Hans, these are Q-Hans, and this is the affine Q-Croucher. And then there's a horrible coefficient in front of it, and a power of Q. I looked at this the other day, and I still couldn't figure out any natural way of explaining this. To write this paper, I had preprints from Andrews and Askey, which showed up in the book, and preprints from Philip Delsart. And it shows to me that you really needed to be in contact with people so that you had a chance to keep up. Looking at this paper, I just did whatever a couple of weeks ago, 48 years. I appreciate the referee. I can barely read this paper myself. The important thing is the Congress in Bar-le-Duc, Polynômes Orthogonaux et Applications. This was the 150th anniversary of the birthday, 9 April of La Guerre in Bar-le-Duc. The organizers, Brzezinski, Dro, Magnus, Moroni, Rondeau. I wouldn't be surprised some of these people might have shown up in some of the photographs that were shown during the intermission of the talks. To my lecture notes, Andrews wasn't there, but if I'm wrong, I'm sorry. But they had a joint lecture, invited, classical orthogonal polynomials, which were sort of, I think, the outline for the Tableau d'Asti and the Q version of the Tableau as well. It is a really good paper and well worth looking at. You will learn a lot if you haven't known it. The conference volume actually has a copy of the Tableau hand-drawn by Lebel of Quebec. I was thinking of copying it, but I don't think my copy would have been third generation. So you'll have to find it for yourself. But it was actually hand-drawn of the Askey Tableau. Here's some of the other talks. Jean Dieudonné, Fractio continuée et Polynômes orthogonaux dans l'œuvre de La Guerre. Wolfgang Hahn über orthogonal Polynome, die linearen Funktionalgleichungen genügen. Walter Gauci, some new applications of orthogonal polynomials. And noteworthy thing is that this is about the time of the proof of the Bieberbach conjecture by Louis de Branche. And Gauci mentioned that he was involved, that he used numerical integration to prove this integral for degree up to 30. And then he found out, I don't remember who contacted who, maybe somebody here has better memory, but Askey and Gasper obviously got together with Dickowski, told them that, yes, the proof is in existence. It was done in 1976. Purdue wanted to throw a big blast for the branch, and they wanted to make sure everything was correct. So they sent out little pieces of mathematics to various people to check. I got the one to check the inequality. George Gasper had a 2-page proof that I got to read and to prove, yes, they really proved it. Some other people that we know who were there, Kornwender and Nabai, Calogero, Titian, Durant, Peter Greiner, Iserles, Marcion, Schempp, Hemi, Ullman, Viano, Jack Wimp. I would say this certainly has something to do with Dick promoting the field, getting a lot of powerful mathematicians involved on it, right? The sideline, sort of my personal story, 77 to 85, astronomers at California, Berkeley and Berkeley labs were designing a new giant astronomical telescope that was going to have a 10-meter diameter mirror. All right, that's more than 30 feet. You can't make that. Previous technology was all one piece. They couldn't do that anymore because it just, you tilt, the mirror gets tilted and it would just change shape, which would be pretty lousy. So they had the idea of putting hexagonal segments individually mounted in a computer-controlled framework. Zernike polynomials were involved in shaping the disk. That nothing was perfect, so they measured the deviation from the ideal surface by an L2 norm with respect to the area. So it's perfect for orthogonal polynomials. They didn't have orthogonal polynomials for the hexagon. Cliff Stoll, who was at the project, wrote to Dick. And Dick said, well, you should talk to Dunkl about it. Well, they did. So I started on this. I used an orthogonal decomposition using the irreducible representations of the symmetry group, which is G2, and then brute force Gram-Schmidt calculation, which was all in rational numbers. At that time, my department had some new mini computer, which was willing to do some giant things. I mean, now you can do it on Maple and your lap, whatever, on your phone for all I know. But the integrals to do Gram-Schmidt, they used some, reasonably sized integers, more than you want to do by hand. It all depended on the fact that cosine squared pi over 6 is 3/4. So the polynomials, they used what's called wavefront analysis. This helps steer the machines that tilt the mirror. It turned out that I was surprised. The mirror is not actually paraboloid like we teach in whatever calculus, hyperboloid. So it widens the field just a little bit. Paraboloid is perfect in one dot. The hyperboloid gives a really good image, a little bit wider than that. Published this in SIAM. That's my only applied math paper ever, but that's okay. My program director at NSF was actually very pleased that he paid for some research that had a real world application. I got to see a mirror. I think this was during the international conference at Berkeley. Each segment is 1 meter. On the outside, weighs 1,000 pounds. Another telescope out there, the James Webb Space Telescope. It's in space. It's headed for a Lagrange point. It also has a segmented hexagonal mirror. Here's a picture of the mirror of the Keck telescope. There's no people on here, but each of these, that's 1 meter. So it's pretty damn big. And I got some pictures off the web of the space telescope. This is the mirror unfolded. There's 2 people there. And this is what it looked like all folded up. I think so far it's been successful. And in the 80s, I got interested in several variables, call them classical orthogonal. I guess that means that, well, you could write down formulas, hypergeometric series would appear. I always thought of Dick as that he could look at abstract series and figure out what parameters you put in there to give it meaning, and then figure out how to sum. And here, again, we mentioned the contour integral for those 4v3 polynomials that Dennis just mentioned before. I was always looking for group interpretations, let's say, opposed to partition theory. Since I was a professional harmonic analyst, professional, I got paid for it. I always wondered about the Gegenbauer polynomials, that we had a spherical function interpretation for half integer parameters. So what's the harmonic analysis for any parameter? Well, my answer was the Dunkl operators. That was sort of the most trivial example of Z2, and yet it turned out to be, I think, it led me to other things there. Somebody mentioned already the summer workshop at Mount Holyoke. I think Kathy Driver did. There was a dinner, and already people were giving Askey anecdotes. And I say why it's hard to give a talk like this one, because I've used up all of my anecdotes, and most of you have heard them, so I already did Askey anecdotes at the dinner. Dick spoke at every occasion. I'm sure I just missed one. Somebody mentioned Irsay. The important one, the Ramanujan Conference in Illinois. He co-edited the Proceedings, which is sort of an impressive hardcover book. There was Hong Kong. There is a NATO conference, Tempe 2000. I think Murad was still at Arizona State at that time. He would ask, he would go everywhere that somebody invited him and talk about it and just say how important special functions were. And you should encourage people who do them too, right? Actually, I think Dick did not go to the Toronto workshop, summer '95, but people in the group did. George Gasper gave a series of lectures. It was a 2-week conference. He was already there in the first week, and I heard he gave homework problems, and then people were rewarded, and Tom was there as well. For me, it was really nice. I organized a session on several variables. I invited and met Yuan Zhu, then we wrote a book together. And I met a teacher I had as an undergraduate, also graduate, P.G. Rooney. And I found out that I didn't know it at the time. He had written papers about the Laplace transform, so he's just another special functions guy. And Murad Ismail did a postdoc with him, I think, in the 21st century. Abramowitz and Stegun, which was sort of on everyone's bookshelf, hardcover at the library and Dover in your own at home. It's worth looking at. People who maybe are more modern than I am. The numerical tables had little things in each column that said you should use this degree of polynomial interpolation so you can get the tabulated precision. Whereas now you just push a button and say, Maple, give me Bessel, whatever it there. But those people actually had tables. So you should look at it at least once to see what the state of the knowledge was. And I think this is still one of the most cited volumes in the field. I found out some of these things because NIST is just up the road from here, Virginia, and I got invited to talk with them and give them ideas. I found out that they never got a copyright on that Abramowitz statement. So they got no money and sell no royalties. And because of that, they couldn't really publish an update. Well, they knew enough not to do that again. So they decided on this project. Here's the 4 fundamental people: Frank Olver, Daniel Lozier, Ronald Boisvert, pardon me, and Charles Clark. They designed the idea that there would be different people writing chapters. There would be validators who would read the chapter and, well, obviously, whatever, send corrections or what have you, and grants. So I have to say, I think I'm not violating my security or anything. I didn't get to do any writing or validating because they needed somebody left over to referee their grants. And so that's what I contribute to the project. I referee grants. They already had very ambitious ideas about what the book should look like, that you should be able to copy text formulas from the book, the graphics. And so they needed not only mathematicians, but some really good software experts. So that was the framework they had, that chapter is validated in software. The gears to find people for all of these jobs. How was Dick involved? I got this from their DLMF page. Askey was a member of the original editorial committee for the DLMF project, serving as an associate editor, advising on all aspects of the project from the mid-1990s to the mid-2010s, when the organizational structure of the DLMF project was reconstituted. Dick was co-author of Chapter 1, Algebraic and Analytic Methods, Chapter 5, Gamma Function. This goes back to my second slide. Remember, I said the special functions course started with the gamma function. And then Chapter 16, Generalized Hypergeometric Functions and the Meyer G function. Chapter in this context, the Orthogonal Polynomials, written by Tom Kornwinder, Roderick Wong, Rulov Kukuk, and Renee Swartau. People I chatted to, grapevine comments, what took so long, delays. Well, there was discussions, negotiations between the editors and the authors. The editors had strong ideas, the authors had strong ideas. It takes longer than persuading one person to finish a chapter. All right, you know the answer? Getting two authors of the same chapter to finish the thing. The hypergeometric functions have now been extended. The original idea was a sum is hypergeometric if the ratio of adjacent terms is a rational function in n. It's a basic hypergeometric series if an plus 1 over an is rational in q to the nth. This is periodic of period 1. The period is 2 pi I over log q. And now elliptic if the ratio of two successive coefficients is an elliptic doubly periodic function of n. Already a lot of important work has been done. Integral formulas, summations, even things with root systems for elliptic series. These are some names, like among others, I'm sure I'm missing some: Spiridonov, Rosengren, Varnar, Rains, coming to the end. Here's some lines from J.R.R. Tolkien. The road goes ever on, down from the door where it began. Now far ahead the road has gone, and whither then I cannot say.
Any questions?
Please say again.
First slide.
First slide.
Yeah.
Page 3 or page 2. I don't know.
Okay.
Page 3.
Yeah,
Is
that's
it-
it. That's it.
Your question?
Yes.
Yeah, no question. I just wanted to know.
Okay. It is an interesting slide, I must say. But I think they will be available online. Murad, yeah, I see you laughing as well. Very good.
Yeah, I hope the photographs also will be available,
Yes, yes,
because
indeed.
there are some I really would like to download. Yeah.
You mean
Yes.
from the intermission? The slides they had from the intermission, you mean, Murad?
No, the
slides
photographs.
they were
In the
showing
intermission,
in the
right? No, you
intermission.
do not have slides. Yeah, I mean,
Yeah.
Okay.
I mean pictures. I meant the ones that.
Graphs of various people at the meetings. Yeah, that was great. The questions.
Yes, Charles, there's not only that DLMF, which was inspired by Dick, but there's also the Askey Bateman project, so it's named after him. And he didn't work in it. He was not an advisor, but the Murad was the big man in it, and then 2 volumes has appeared now.
I know. I thought that would be just promoting myself. I didn't say anything, but you're right. It should have been mentioned.
Yeah. Any other questions for Charles? I see you great on the full screen now, Charles.
Hello, Donald. How are you?
Good, good. I feel better knowing that I failed chemistry in high school. Yeah, I actually failed it. It was the British O-level exams, and I got a
Yes.
I got a 7, which is a near fail. And of course, physics, I was not allowed even to come to the labs after 3 weeks. They said, we don't think you belong here. Go someplace else. So I feel better now.
Oh, I did pass first year college chemistry with a B. It didn't help that the professor had an artificial hand.
Yeah. Yeah.
Okay, this guy is a serious chemist.
Right.
Or else
Yeah.
he did freshman lab and some freshmen blew him up.
Any other comments or remarks?
I have
Well,
a question.
Go ahead, Howard.
So Charles, do you envision any future for addition theorems?
You would need some more Gelfand pairs. I think all the one variables have been pretty well found. I think that presumably there could be several. And I think some of the work is more in the context of quantum groups that Tom would be able to give, I think, an expert opinion on what might be expected from quantum groups in terms of addition theorems.
Well, I think Erik Koelink is even a bigger expert on this. I don't know if he's in the audience, but I would also mention the dual addition formulas that I have started some 5 years ago. Now I've done 2 cases, but there are some more evident cases which I'm too lazy or too old to do. But until now, nobody else have picked them up, and I'm very much hoping that there will be some more work being done on this.
So there are, it turns out that addition formulas for the hypergeometric functions of matrix argument show up in the engineering research on wireless communications. So there are people, I'm actually working with 2 people in Japan, Kimichi Takemura and Satoshi Kuriki. And by writing out the addition formulas for the confluent hypergeometric function Hermitian matrix argument, use those formulas to solve some problems that the engineers have been trying really hard to understand. So yeah, so there's a bright future for addition formulas. Yeah.
Thank you, Donald.
You're welcome.
Any other comments or remarks? Well, let us thank Charles once again.
You may have noticed that I turned off my camera almost just before I was supposed to start. I was looking at my picture and I had on a shirt which was causing all sorts of optical patterns running across it, pinstripe shirt. And it's like, oh my gosh, people will say, turn off your picture. So I swiftly ran and got another shirt on, which doesn't do anything bad.
Yeah, no, it was good to see you, even if only virtually. And a very interesting talk. Thank you.
Thank you, Kathy. I would, since you're all here and Kathy's there, at the Askey 80 conference, I was one of the people stranded at the airport, and and I was pretty disgusted to find out that I got home a day after both Kathy and Roderick Wong got back to South Africa and Hong Kong, and I spent 2 nights at O'Hare.
Yeah. But I think it was a measure of, certainly in my case, of my gratitude to Dick to go so far for a 4-day conference in his honor, his 80th birthday. There were a lot of interesting people there. Martin Muldoon came, and there were a lot of good discussions and some wonderful photographs, but it was a huge tribute to Dick, I think. I don't know if you would agree, Charles, that a lot of people went a long way to say. Oh, yes. I didn't mention it. I thought, well, so many people who are here were at that conference and know so much about it. What could I say? Yes, we had a dinner. Again, we had an evening of anecdotes, which again makes it harder to tell another anecdote. But yeah, it was a great meeting, certainly. Alan Sokol was there as well. Yeah, a lot of people that have been attending this. I think Dennis organized it. He would have the list of people who attended. I couldn't find it in my notes. So I thought, well, I would just not do it. But Dennis knows who was there. Indeed. Yeah. Yeah, it was a great tribute to Dick, and it was very, very cold coming from South African summer into December. It was hectic, very hectic. Well, thank you all, and great to see you all again. And I hope it won't be too long before we have some face-to-face conferences that we're all attending. So Thank you, everyone. I think that's it, Murat, unless I'm very much mistaken. Am I wrong? Hang on, I may have only written down that what I was chairing. I
No,
have
Donald
the
is going to talk at 3:15.
Ah,
Yeah.
okay, okay.
Yeah.
So 3:15. Okay.
Yes, okay.
I had to
And
work out
then-
a 6-hour time difference. Okay.
And
Yes,
Paul
thank you.
Levi is talking at 4, Sean Cooper at 4:45.
Okay. Thank you, Charles.
You got that right. And Howard is chairing. Very good.
All right. See you
Thank
soon.
you, Luke. Thank you.
So we can have a little stretch now.
Okay. Thank you.
Good.